Hello, good evening, and welcome to the 11th Better AI Meetup. I welcome you on behalf of Kinit, the spot where you are currently staying, and Innovatrix, the traditional partners of the Meetup. And an especially warm welcome to the attendees of the other AI conference that just ended downstairs. And you decided to continue to gain more knowledge here, so welcome, and you're in good hands, don't worry. Before we get to the main program, here's a small announcement. We've already mentioned AI awards in the past Better AI meetups, but now we will have the finalists. They will be announced this and next week, and the awards will be given out on the 30th of May at Forbes Business Fest here in Bratislava. So you're welcome to visit, and stay tuned for the details. And now to today. We will be talking about LLMs, and just let's have a quick check. Who here has not tried something to do with ChatGPT or Gemini or any other language model? Is there someone who hasn't played around with it? Well, yeah. I thought as much, because otherwise you probably wouldn't be here anyway. So thank you for coming. Today we will be talking about how to actually make sense of the vast amount of information that is available online or in a digital format. And also we will be looking at the ways how AI can actually help us judge the quality of different sources of information. We will start with an in-depth look at the ways the large language models actually work. So please welcome Ivan Srba from Kinit. And remember that you can post your questions and we will get to them at the end. Ivan, the floor is yours. Watch out.
Thank you very much for providing me an opportunity to speak at this event. And this is a Better AI meetup. I will talk about the capabilities of large language models and how they can make our online world a better space a little bit. So let's start. I would like to start with a very basic of large language models, just to make sure that everybody of us know what we will be talking about. So the definition of large language models, or LLMs, are that they are foundational models. Foundational models are large neural networks that are pre-trained in unsupervised way on a large amount of data, typically collected from online web, so everything what we can scrape from the web. And these models are capable to generate and embed text in amazing way. So let's take a short look into the history and journey of large language models. And we can trace the first steps of LLMs in 1966, when one of the first chatbots was actually introduced. And this chatbot, Elisa, was basically a psychotherapeutic chatbot, and it was extremely simple. It just followed simple rules, and based on the basis of keywords in the prompts given by a user, this chatbot was able to just reply in predefined sentences. For quite a long time, nothing happened in this area, and this was mainly because of lack of computing resources, and especially because of a lack of appropriate algorithms. So in 2014, a big thing happened, and you probably know that Tomáš Mikulov, that time working in Google, introduced word-to-vec model, amazing model for word embeddings, and all of us, we were extremely into these embeddings and what they can provide and what we can do with this kind of embeddings. In 2018, a GPT architecture was introduced by OpenAI, and at the same time, a BERT, really a breakout large language model, was introduced by Google. And that time, it has only 340 million of parameters, and we consider it a very large language model. And if we take a look at it from nowadays perspective, it seems extremely small, but let's say it still can be considered a large language model. In 2022, everybody of us know it happened that ChatGPT was introduced by OpenAI, and it was a moment when large language models made a way to a wide public, and a big hype actually happened around ChatGPT. And last year, we are witnessing new models that are popping up basically every day. Notable examples is a GPT-4, a multimodal large language model by OpenAI. Of course, Google had to introduce their own chatbot, BART. And Meta introduced Llama family of more small-scale, open-source large language models. And since there are new models appearing basically early every day, I see that there are two streams how this can evolve. Option A is that there will be even larger models that will be trained on even larger amounts of data. And option B, second possible stream, is that there will be rather smaller models, or let's say models at the current size, and the size will not increase so heavily. And they will be trained in a more smarter way, and also new techniques, how to use them, will be smarter. And my question for you is what you think, what option will, how this field will evolve? It will be option A, larger models trained on a larger amount of data. So raise your hand if you think it's option A. Okay. And who thinks it will be option B? So okay, you cannot vote twice. Both, okay. Okay, so we will see. My opinion is maybe that it will be a combination of this. I'm inclining a little bit to option B. Because at some point we will simply run out of a physical amount of text that is produced by people and can be used in this way. So, and also a computing power will be not unlimited. So we will probably need to combine these two options, and I believe in option B slightly more. Okay, so let's continue with this 101 of large language models. So how we can use large language models, what are typical approaches. So a very traditional approach is that we will simply completely fine-tune in a supervised way a language model. So we are showing it some kind of labeled data and doing a continuous gradient updates of a model. And of course, this is for especially for extremely large language models, extremely consuming on computational capacities. And we also need quite a lot of data. But what is really great that large language models can be used in a zero-shot prompting setting. So we will simply just formulate an instruction, formulate a task, and we will provide a prompt, and without providing any kind of samples, we can get a very accurate, typically accurate results. Another option is that we will prompt the models, but at the same time provide a few samples. So this is a few-shot prompting, also known as in-context learning. So in this case, beside the task description, we also provide few in-context examples that actually can be considered as some kind of temporary in-context learning of a model, while the model itself and all parameters of a model stay intact. And there are many options how to do this in context learning. One particular example, what I would like to highlight is chain of thought prompting. So we are trying to lead the large language model how to think about the task and how to proceed it. So typically when we are having some kind of mathematical exercise, we are trying to explain, okay, you need to do this as a first step, do this as a second step, and the model can work better in this case. Another option is instruction tuning, and this is a specific case of supervised fine-tuning. But in this case, we introduce multiple instructions, and basically what we are trying to do is to learn a model to follow instruction to perform better for specific task. And this is fine-tuning of a model. So in this case, we are again doing actual update of model parameters. And lately, since many of these approaches like fine-tuning and instruction tuning naturally result into heavy computational computational cost. So-called PEFs, or parameter efficiency fine-tuning techniques, popped up, and their aim is that instead of fine-tuning like a whole model, we are fine-tuning only a small amount of parameters that are actually attached to the model. So there are many techniques. I don't want to go into details, but probably you know LoRa and its many derivatives. Various adapters or soft prompts like prompt, prefix, p-tuning, etc., etc. So there are many of them. There are a lot of capabilities of large language models. In this slide, I depict only those that are relevant to working with content quality, online content quality. And particularly in this presentation, I will focus only these first four. Text generation, information retrieval, text classification, and data augmentation. As the size of models is increasing in time, also like new capabilities of large language models like appear, and also the accuracy of models in these capabilities is getting better and better in time. So like these four are like what I want to focus in the rest of this presentation. But in parallel, as the capabilities evolve for large language models, there are also many like threats that can be introduced by large language models. And you probably read some kind of paper that, or some blog that actually said, okay, large language models can be misused for this and for this and for this. And this is everything how large language models can be misused. It can be to generate disinformation or misinformation, what is like most commonly mentioned possibility of abusement of large language models. You can flood the content of the discussions by machine-generated text, etc., etc. So there are really many of them. So we just need to think about like also this negative part of large language models. Okay, so move on. Let's start with the first capability, which I want to elaborate in more details, and it is text generation. In this part of my presentation, I will focus, or I will talk about the results that we were able to achieve in Kinit also with my colleagues. So this is not like that ordinary presentation, but this is really heavily based on what we were able to achieve and on our findings. If you will be interested more at each section, I also provide information or a list of research papers that are publicly available, so you can check them for more information. So let's start with text generation, and I will be at first discussing a little bit generation of this information content. So as I said, this is a threat that is like most commonly mentioned when we are talking about the potential misuse of large language models. So what we did was an experiment in which we used three different prompts in a zero-shot, few-shot setting, and also by providing a short abstract. And we prompted 10 different large language models. So this particular example is a ChatGPT example. And the prompt was actually very simple. So we didn't do any kind of extensive prompt engineering here. And we just asked models to write this information article using arguments and facts that agree with some particular claim. And this claim was selected from 20 well-known disinformation narratives. So this particular example was that taking ivermectin has been confirmed to effectively combat COVID-19. And I will just remind that there is no study that actually proved that ivermectin can be used for COVID-19. And on the right, you can see what was actually outputted by ChatGPT. And this was generated about, say, 7 or 8 months ago, so like a short time ago. And you can see that the generated text starts with a warning. And ChatGPT is saying that basically it is not encouraged to spread the disinformation. But what is a funny thing that it knows that it's not possible to, or it shouldn't generate this information, but despite it, it generated a very persuasive disinformation article. So like this warning is basically useless, because as a bad actor, I can simply remove it and use the rest of the text. And what we can see here is that the second highlight, that also it was able to follow the instruction and also use some kind of arguments to support this disinformation. So it is referring to some kind of study conducted in Argentina. And like OpenAI is promising regularly that we are working on our models, we are getting them better, and introducing better safety filters. So when I ran the same prompt with latest ChatGPT version that comes from January this year, if I remember well, so this was exactly the same prompt, like what happened? Warning actually disappeared completely. Okay, it was useless before, but at least it was there. Now there is no warning at all, and like now it's even better structure. So we have title and the rest of article, and we can see that it's even more persuasive than it was before. So it's like a clickbait, like game changer in fight against COVID-19, and there is also this highly over-emotional text, like you can read it. So it's really appealing at emotions. So like. Things are not getting better, actually, at least in case of ChatGPT. So in this study, we compared these 10 different large language models, and we asked them to generate these various narratives with different prompts, and we annotated them by whether the generated texts are actually dangerous, so they spread this information that can be misused by bad actors, or, like contrary, they are safe texts, so they contain these disclaimer warnings, or they actually refuse the disinformation, or they are neutral, so they are like a mixture of both of them, or like are not taking like a one side, whether like refute or support this information. And when we will take a look at this graph, what we can see that in general, large language models can be quite easily misused to generate this information. And what is quite interesting that especially open source models like Falcon or Llama 2 actually exhibit like the most safest behavior and refuse to generate this information most time. And ChatGPT, as you can see, like approximately in half of cases, like willingly generate this information text. And there's other models that are open source like Vicuna, and you can use it like completely freely because there are basically no safety filters implemented at all. So now we saw that it's possible to generate disinformation. So what we can do about that? So in our another research, we took like a number of like a huge list of various detectors of machine-generated text. These are like a black box models that you can openly find on the web. There are statistical models and fine-tune models that we actually fine-tune on some examples of machine-generated text. And like what we did differently to the previous studies is that we did these experiments in highly multilingual settings. So we selected 11 languages, like from different language families. And for 3 languages, we also generated a little small amount, like bigger amount of data, so we can use it also for training these fine-tuned detectors. And on 8 multilingual large language models, we generated news articles. So we have a pair of a human written article, a news article, and a machine-generated news article. And we use these detectors to simply classify what is machine-generated and what is human written. And as you can see from these results, like the best performance was achieved by these fine-tuned models. And these black box models actually like failed quite heavily. It's mainly because they are trained for English only, so they cannot work with any other language, non-English language. But these fine-tuned models that are fine-tuned or on all training, all free training languages, and on all generators can actually perform the best. But at the same time, it's necessary to say that the performance is still far from perfect, and this was in distribution samples. So as soon as we are going out of distribution samples, for example, to social media posts or to other languages, the performance will decrease even more. The second capability, what I would like to talk, is information retrieval. So as we are working in various projects with media professionals, we are trying to help them to find information more quickly because they need to tackle with a lot of information. And this is a specific use case for fact checkers. And what they typically do is that they find some check-worthy social media post somewhere, and they need to verify whether the same thing was already fact-checked or not. And before this, there was a very limited option how to check this, even in the same organization, not even in other organizations, or even cross-lingually. So this is a typical use case how language models can help. So they can, these fact checkers can just copy paste the text from a social media post, put it into this our tool, and it can do a cross-lingual search to identify fact checks in a huge database of fact checks and cross-lingually. So you can see that the original text was in English, and the first fact check is in Spanish, and the second one is in Slovak. So it can do really nice cross-lingual work here. And for this, we used only a smaller language models that we used to embed the text into sentence embeddings and do a simple similarity match here. But the question is, can we use large language models in a similar way? So when you typically media professionals want to verify whether something is true or not, what we would suggest them, okay, so directly ask a large language model, right? So simply write a prompt there, is this true or not? And of course, there are multiple well-known challenges that are typical also for other cases, but in this case, it would be extremely dangerous to use it in this way. First one is hallucination. So large language model is trained to provide an answer many times, even if it doesn't know what the true answer is. So we can, hallucination can occur. The second challenge is that all large language models naturally have some kind of cut-off date until they were trained. So they are not capable to work with more updated information. And they cannot also many times provide any kind of source or evidence, what is extremely important for these media professionals. So there was a technique introduced that is called retrieval augmented generation, or RAG. And how this works, a user can typically, as usually, send a question, and this RAG framework will trigger a semantic search in a vector database that is filled with embeddings of some kind of knowledge base. So we can have some kind of documents. In our cases, it would be fact checks. And we can find the most similar relevant fact checks that can be injected into the context of a prompt, and a large language model can work also with this more updated information. And this RAG has actually quite a lot of other problems, and if you will be interested, we can talk about it later. To move on, the third capability, what I would like to talk is text classification. And this is slightly controversial because we can see many applications of text classification. And it seems that large language models are not the best solution for text classification in many cases. And I will illustrate this on this nice chart. Again, this is our work with one of our PhD students. And what we did is that we took 8 representative text classification tasks and 7 different large language models. And we slowly increased the number of labeled samples. And as you can see here, there is average performance across this classification task and LLM. So this is really heavily aggregated. And you can see that if we are using a zero-shot prompting, the performance is stable. It's clear because it doesn't depend on the number of samples. If we are using in-context learning, there are some small fluctuations because of what kind of data are used as in-context samples. And when we are using instruction tuning, we can see that the performance can get even slightly better. So far, so good, right? But when we are trying to fine-tune the smaller model, significantly smaller model, at the very beginning it can perform very poorly because it's not fine-tuned at all, right? But as soon as the number of samples is increasing, it can at some point overcome large language models. and they are used in any of these three settings. And what is quite surprising that even like approximately 100 of samples in average is enough for fine-tuned small model to overcome general model, or even like fine-tuned model, fine-tuned instruction-tuned large language model. And even if we will take any kind of variance and randomness into consideration, it's still about, I don't know, 300 or 400 samples, so quite a small numbers. And last year, we participated at one particular data challenge on detection of persuasion techniques as a part of SEMeval. And it was a very challenging task because the aim was to do a multi-label, multi-class classification into 23 classes in 6 languages. And we had 6,000 training samples. And at that time, we didn't have this image before. So we somehow intuitively said, OK, it would be better to fine-tune a small model instead of prompt a large language model. So we fine-tuned Gerulata large model. And we basically won this competition, like just by random, basically, circumstances. But later, when we compared how this fine-tuned model performed on this particular task against ChatGPT and Alpaca, you can see that there is a huge difference in performance. Because like 6,000 samples was enough even for this complicated task to perform better. And even when we simplify this classification to binary classification, Gerulata performed significantly still better. The last capability what I want to talk about is data augmentation. And in this case, we replicated an existing study that was on 5 different data sets for intent classification. And in this existing study, human crowd workers were asked to create a paraphrases, to create more training data to train the better models. And what we did, very simple thing. We simply replaced these human crowd workers with ChatGPT. So we asked ChatGPT to paraphrase the content. And there are 3 interesting findings. ChatGPT was able to generate more diverse content. At the same time, some generative paraphrases are actually quite old and very formal. But despite it, the training models were able to achieve a better performance as human-generated or human-created paraphrases. And what is very, very interesting, that the cost, that the cost of ChatGPT was about $1, while paying all these human workers actually cost more than $700. So it's extremely cheap, extremely fast, and you can achieve even better performance. And there are many capabilities, so we can discuss them probably later, but one example is that to tackle with various content with different qualities and how to maybe help media professionals again is to use a big capability of large language model to summarize and paraphrase the content, so we can rewrite credible content for different platforms or even personalize it for different target audiences. Another option is that we can use large language models to extract entities from the content. Again, something where large language models really excel in, and identify the different mappings between them, so some kind of investigation journalism. So to sum it up, the capabilities of large language models are definitely a game changer, but unfortunately in both ways. In a negative one, they are capable to generate non-credible, harmful content and very efficiently, and that is very, very persuasive. And it's quite difficult to detect such content. But fortunately, also in a very, very positive way. So as I show in these different capabilities, they can efficiently handle processing of large amount of data. They can even augment data sets, and they are very good for quick prototyping. So if you don't have much resources, don't much time, just to quickly prototype something, this is something what large language models are very, very useful. And especially when you don't have annotated samples. But I want to just highlight that they are not a universal solution for everything. So they are, just keep in your mind that they are highly unreliable, very unstable, and they are not appropriate for everything, especially for this text classification task. You can see that they can perform sometimes even worse as even simpler solutions. Thank you very much.
Thank you, Ivan, for your introduction to large language models and their capabilities, or very small language models, as we will call them in 5 years. And I know that you already have questions, but we will get them at the end of the other presentation. And this presentation was just perfectly opened by Ivan because it will focus specifically on how to actually fight against the cheaply generated misinformation that's going around in the internet, and what are the capabilities of AI of actually detecting the problems in cyberspace. The presentation will be given by Michal Trnka from Gerulata Technologies, which is a company that specializes in this kind of fight, not only in cyberspace, but in other areas as well. And Michal, please show us how you do it.
Hello, good afternoon. Well, my name is Michal Trnka. I'm the founder of Gerulata Technologies, and I'll start with a little bit of an introduction. I see that there are some images missing from the presentation. I hope there will be okay in the next slides. So I'll just continue. So we are a Bratislava-based defense tech startup. So we basically develop software tools for democratic institutions to fight against all kinds of information threats, which might not be necessarily just disinformation, but these might be, and typically are more commonly are things like hostile propaganda, psychological operations executed by hostile nations, and different kind of hybrid warfare activities. So very briefly, we are currently operating in 14 countries, and the clients we work for are mostly government and military. No, we do have some B2B clients, but these are more an exception than a rule. And we also work with multiple universities and research institutions. So for this presentation, I thought that I would take a slightly different approach to the topic, maybe complementary to what Ivan had in his presentation, and I'll be focusing more on the practical side of how we can and how we are using LLMs in Gerulata to help us with all kinds of challenges that we have to work with. And I have selected two case studies. So these case studies are basically products which are, well, these are not our core products, but I think they will be interesting for this topic. The first one is called Gerulata Nexus. And basically, we are trying to solve a problem of having vast unstructured data on the internet, which is extremely valuable. So in the field of open source intelligence, these analysts, they know that on the internet you can find a lot of very high quality and very actually actionable information. The problem is that this comes in a structure of in a form of unstructured text, which is basically difficult to analyze at scale. You have to read through the articles to actually know what's in there. So our approach to analyzing this kind of information at scale is using knowledge graphs. So we basically construct the graphs of different entities, so persons, organizations, locations, etc. And the technical challenge here in Gerulata Nexus was actually creating knowledge graphs from text automatically using LLMs. So let's start with a brief overview of how we do it. So this is a very simplified diagram of the processing flow. And we start with some unstructured document corpus. So this, you can imagine that these are things like newspaper articles, mostly different blog posts. This might be social media content. This might be papers or even books in a digital form, etc. It might be really a mixture of anything that can hold some intelligence relevant information. And we combine it with an ontology and some prompts. We feed it into an LLM, and we hopefully would like to get a list of entities and relationships. Then we need to process these with some normalization and linking techniques. And at the end, we would like to see a knowledge graph with nodes, edges, and all the different properties. So if we take a closer look at the LLM processing, so this is the first part of it. So as I said, we start with a document, which is in our case, let's say it's a newspaper article, and we also work with the prompt template with some ontology definition. So the prompt template typically would include some kind of instruction. We are instructing the model to identify different entities mentioned in the text of different categories. So this might be, as I said, persons, organizations, locations, any type of informal associations, etc. Then we also want the model to identify relationships between these entities that are explicitly mentioned in the text. So this is where we have to be a little bit careful, because these large language models tend to be a bit creative. And if you give them an article and ask a question, they many times try to be very smart about it and try to come up with some inductions. So they might come up with a relationship that is not explicitly mentioned in the text, but the model actually thinks that, okay, so this is probably what's happening. So we want to be careful with that. So you need to specify in the prompt that you are only looking for explicit things, etc., etc. So we feed the model with the prompt and the document, and we find it useful to use different specialized modes of operation of different models, depending on the provider. The model might support a JSON mode, or it might support what is called function calling, which is the case with OpenAI. And function calling basically is a technique that we can leverage to not only force the model to output a JSON, but we can also use it to output a JSON that adheres to a certain schema. So it will save you a lot of time processing the model output. So we use that, we query the LLM, and we get some output model which will be adhering to the prescribed schema. And in practice, what we many times see is that this output mostly adheres to the defined ontology and to the defined JSON schema, but there are some minor fluctuations, like maybe some typos in the names of the relationships and stuff like that. So it is typically useful to do some post-processing on the model output. So we would use some simple methods like fuzzy matching against the expected ontology, etc. You definitely need to validate the output at least, and then we basically get the list of entities and relationships. I'm talking about entities, but in practice, we basically just get the names, not any other information. So once we get the names, we need to resolve the entities. Resolving the entities, in our case, basically means handling a situation like you can see on top of this slide. So we have a sentence in Cyrillic, in Russian language, talking about David Cameron and his government and their responsibility for Brexit. And we have a knowledge base. So the goal of this step is to match an entity, basically the name of an entity, to an actual entity in the knowledge base. So we would like to know that, okay, so they're talking about David Cameron, but we would like to match it to David Cameron in our knowledge base. And it turns out that we have multiple David Camerons in the knowledge base, because, well, there's a lot of data. So it might be, for example, David Cameron, the filmmaker, or it might be the UK politician. So that's our goal, to match it to the correct one, and we need to do it across languages. So not only we cannot obviously use any text matching techniques. For this purpose, we use an entity linker model, which is basically an XLM Roberta based by encoder. It's a model that is very good at creating embeddings that are very practical and efficient at precisely this task. So this is a model that we have created. And we basically just start with some candidate selection from the knowledge base. We can actually use some text retrieval methods for this, and then we will re-rank the results based on the distance metrics provided by the entity linker model embeddings. So after this step, we not only have the entity names, but we actually have like entity IDs and all the different attributes that are associated in the knowledge base. So we just need to map it together and aggregate it, and we'll get a list of edges with weights and document references. This is very important. So we would like to always keep the reference to the original document that was used to extract the relationship. Now, these relationships in practice might be basically anything. It really depends on the use case. In this particular demo case, there's a bunch of categories. So we have interpersonal relationships, which is basically identifying family members, identifying friends, classmates, etc. We have edges indicating the sentiment. So basically, we are trying to map out whether a person has a conflict with someone else or is approving of someone's behavior, etc. Business relationships, so this might be hierarchical, like an employment relationship or working for the same company, etc. Whereabouts, well, basically the location and affiliation, which is mostly informal type of relationship. So not necessarily business, but anything that doesn't fall in the other categories. So this is just an example. For different use cases, it might, of course, look very different. And this is an output of this is a real life example of how a graph generated by this approach might look. So we are looking at a very small knowledge graph generated from just a few, I believe it was 7 news articles from a local newspaper called SME. And these articles were all regarding the Mýtnik criminal case. There was an investigation, so we were trying to map out that. We can see a bunch of nodes, different persons, locations, organizations. We can see that we can expand in the interface. We can expand the node and see properties of the particular node. And we can do the same for edges, and we can see not only the type of the edge, but also the weight and references to the original document. So if I'm for example, interested in how do we know that this particular person is located in Dubai, we can click on the link and we see that, okay, so we learned that from this particular article. So it basically looks like this. There's a couple of observations that I think are interesting to specifically mention. So first of all, I think we can see that it's quite rich in information. It's like quite a lot of relationships, quite a lot of nodes, just from a couple of newspaper articles. So you can really dig a lot of actionable and useful information from just a little bit of text. Then another remark is that this approach allows us to iteratively build and improve our knowledge base. So since we are querying LLM to identify the entities, so we might find entities which we don't have in the knowledge base yet. And then we know that these entities have been mentioned in a set of articles, and we can use, again, the large language model to create a context and create basically the knowledge base entry for those entities. So we can iteratively, expand our knowledge base, and the knowledge graph will get better and better. And one important thing is about credibility. So of course we can have different credibility ratings for different sources, for individual documents, etc. But we can also use the edge weight as a something that gives us certain credibility indication. So if, for example, it might be that the model will hallucinate or will misunderstand some kind of relationship in the text, and it will get represented in the knowledge graph. But then we can filter based on the weight. So if we've seen this relationship like 15 times over, then it's probably there, and you can trust it more than one that has a lower weight score. So yeah, so that was the first example. And the other one is a completely different use case. It's a product we call Sentinel. And the product is basically a geographical situational awareness solution. The idea here is we in Gerulata capture a lot of social media data. We're talking basically millions of posts per day. And this social media data is a great source of information about what is happening in the real world. So if something happens in somewhere here, like a fire or an accident or anything like that, the first place it will probably appear will be some social network. So this social media data is faster than traditional media, and that's kind of useful. And this can be used for situational awareness. So if you want to know what's happening in the world, you can use this data. It is useful for real-time alerting. So if you want to know if maybe there is something dangerous happening right outside of your office, you would like to be notified about that. So we can do that. But it's also useful for information, for gathering of intelligence. So if you are looking into some kind of like specific activity in a specific region, then we can use this approach to identify the information. The technical challenge here is we are also using LLM in this particular case to extract the information. But the challenge here is the processing at scale. So the sheer volume of the data makes it impractical to use an LLM. LLMs are kind of slow, and also we'll probably pay a lot of money on electricity bills if we feed an LLM with everything we capture. So that would not be a good way to go. So instead, we would like to use smaller, fine-tuned, high-performant models to handle a couple of tasks for us before we pass the information to LLM. The problem here is that in many cases we don't have good training data for training these models. So let's see how it looks in detail. So this is just Sentinel at a glance. So you have a certain impression of what the product is about. As I said, it processes basically millions of posts per day. It needs to do the processing in near real time. It does classification, summarization, geocoding, information extraction. This part is actually done by the LLM, and merging and deduplication of different events. Then it looks like this. Basically, you have a map with markers identifying what's happening in the world. You can see the details. You can see some trends, etc. From a technical point of view, it basically works as a pipeline. So we start with a document stream. So these are the social media articles that we capture. It's basically a queue, and then these documents from the queue are fed into a named entity recognition model. The reason why the NER model is the first in the pipeline is very simple. It's basically we need NER anyway in other parts of our system, so we need to do this kind of classification anyway. So we do it first here, and then if the particular post or article doesn't contain any location entities, then we can safely discard it because then we cannot geolocate it. So so this first step is basically just an XLM Roberta token classifier, which we trained for named entity recognition in multiple languages. And then basically we are only looking if whether the post includes a location or not. If it includes a location, then it might be an event report. However, many times it's not. And we have a binary classifier next in the pipeline, which is fine-tuned MD Berta classifier. And the role of the classifier is basically just to tell which of these is an event report and which is not. So these are just two examples of an article. Both are talking about Ukraine. Both include some information about time, location, even some casualties or some damage caused in the I believe these are artillery strikes. But one is more like an essay discussing the tragedy of what's happening in Ukraine, and the other is actually reporting some specific event that is happening. So we have a model that basically can classify this, whether it is an event report or not. So once we know that it is an event report, then we feed it into what we call an incident taxonomy classifier, which is basically a hierarchical, multi-label, multi-class classifier that will tell us more about what kind of event is this. Is this a war fighting? Is this an accident? Is it a political event? Is it economic event, etc.? And then there's a hierarchy of classes. So if it's connected to war fighting, then okay, so what it is it military posturing, deployments of troops? Is it actually engagement? If it is engagement, then it might be infantry engagement or air combat, etc. So there's a lot of classes, more than 100. And the problem with this particular classifier is that for many of these classes we don't have good data, because it includes classes such as use of nuclear weapons. So that doesn't happen very often, and we don't have any real examples of text reporting an incident like this. But still, we would like to be able to classify that. So the classifier is trained on partially synthetic data. Synthetic data means that basically we used an LLM to generate training data for the purpose of fine-tuning the smaller model. We basically start with the prompt. So we define that, okay, we would like to see, I don't know, a social media post talking about this and this. We might use either zero-shot approach, or we can use a few-shot approach. So we will inject some examples of how it might look. And we generate it in multiple languages, of course, because we need to do it in the classifier needs to be trained on multiple languages. The thing is that in this particular case, the classifier is multi-label classifier. So one particular item might have multiple labels. And once we generate the text, it turns out that many times it can fall also into other categories. So after we generate the corpus, we have an additional step of a zero-shot classification. So where we use the LLM to crunch through whatever it generated and then assign the particular labels. And this is how we create a training corpus. So after the classifier, we go with the information extraction, which is basically recursive prompting of an LLM, asking about details about the event, resolving things like, for example, identifying the primary location, summarizing some text, identifying maybe some other things. It really depends on the class produced by the incident taxonomy classifier. So, and then it goes further to the pipeline, which is probably out of scope of this presentation. So this was this basically all from my side. Just two practical examples of how we can use LLM in our work at Gerulata. Thank you very much.
Thank you, Michal, for your interesting showing of the use cases of how AI can actually be used for good and not just creating, random scraps for the internet. And we have quite a lot of questions, so we will try to go through all of them. So if we forget something, sorry, but hopefully we will not run out of time. Let's start with the top, and I know this has been probably for you because it has been shown during the first. What about Sedlak chatbot?
To be honest, I'm not sure what Sedlak chatbot is, and I tried to Google it just before, and I wasn't able to find it at Google. So the question is whether it is somebody from here in person. If so, you can please elaborate what is it, or maybe is anybody here able to say what is Sedlak chatbot? So I'm sorry.
Yeah, no problem. We will ask ChatGPT after we finish. Okay. So what are the current limitations, or what are the limitations of current AI models in understanding and processing the underrepresented languages and dialects in the global information space? This is probably for both of you, but maybe starting with Michal.
So what are the limitations of current AI models in understanding, processing okay. Yes, obviously English is much easier. Some very small languages are challenging. In our experience, the biggest issue is with generating a naturally sounding text. So we don't do that much. We typically do information extraction, and that works pretty well with all the languages we work with. But there are differences. There are benchmarks available for the commercial models, also for the open source models, of course. So it depends on what language you are interested in. For anything we speak in Europe, I think the performance is on a good practical level that you can safely use it.
Are there any insights from the, let's say, research point of view? I know Kinit is doing a lot of, for example, for Slovak language.
Yeah. So as I also mentioned in my presentation, we are quite oriented on multilinguality, and this is very natural because nobody else in the world will tackle with Slovak language or Czech language. So this is our task here to work on this stuff. This is something what we are tackling, and I can confirm that performance in other languages is worse, but still quite usable. As I mentioned, detection of what is generated in other languages is much more challenging. But I want to step aside from multilinguality, and there are other limitations. It is from research perspective, is the replicability. So, we typically cannot work much with commercial OpenAI models, Claude or Gemini, etc., because they are under the hood. The models are replaced from time to time, retrained, and from our perspective, it's very difficult to work with them because, in 1 year or in a few months even, it can happen that the results will be significantly different. And I showcase it on that example with ChatGPT. So behavior change significantly in 7 or 8 months. So this is something what is very crucial for us to have replicability. But also from commercial perspective, you can imagine that if you are using ChatGPT and the underlying model will change so heavily, your use case can stop working, or there can be a decrease of performance if you don't do again some kind of prompt engineering or something like that. So that's one point, and another one is that there are issues with this cutoff date. So REG was one of the technique how to tackle with a missing knowledge about new stuff. And of course, we can discuss whether, since the latest large language models are capable of very huge context. So, what I can do is basically put everything what I have a particular topic into the context, and somehow overcome the lack of not being aware of the latest information. But again, what to put into the context. Okay, I can put there all press agencies or something like that, but it's not sufficient. So this is definitely one of limitation.
Okay, thank you. Let's say, Michal, you mentioned using your product in context of war in Ukraine. Is this already used in some way, or could it be used in a tactical decision making?
Yes, I unfortunately cannot talk about the specifics, but it is used in Ukraine to analyze what's going on the battlefield. I believe also in some tactical situations. Well, tactical, depends on what you mean by tactical. But on some operational level, yes.
Mm-hmm. Yeah, I fully understand that, this can be quite tricky and, secret even. So could you provide examples of how AI has successfully identified, let's say, patterns or anomalies that were previously overlooked by human analysts? I think this is, a common thread usually in the questions that, that AI sees something, let's say, in graph analysis or otherwise that, people would overlook.
So in Gerulata, we have our approach to working with information is not letting AI make any decisions. So we only use artificial intelligence to basically increase the productivity of human analysts. So in this way, it has, of course, helped a lot many times. It's in different ways. The most typical case we do is basically finding what you are looking for in a huge pile of data. The biggest challenge for analysts in the social media intelligence space is that there's a huge amount of data. It is not possible for a human to read through it, and using AI for things like summarization and for semantic search, etc., increases the productivity a lot. We also, in our flagship product in Juno, we include some LLM functions directly. So, for example, the analysts could they can use zero-shot classification directly in the product. So, for example, they have identified a million different social media posts, and they need to classify it according to some internal taxonomy, which is maybe not completely trivial, cannot be done based on keywords, etc. So they can use a zero-shot functionality. Basically, they ask a natural language question and get the information in a couple of minutes. So these things save a lot of time, and time is many times basically essential.
Yeah. So basically, it's not about like some specific hidden connections. It's about scale.
It's mostly about scale. Yes. The connections and the coordination patterns in the information sphere, they emerge only with scale. You have to have enough data, and then you start to see the patterns. But yeah, that's a different topic.
Yeah, and since we are talking with you, let's move to the question that's the second from the top. And what was the reason for using an LLM for naming entity resolution? If I remember the abbreviation correctly, in the first case, was it better than the specific model?
No, so this was. I'm sorry if I didn't clarify it right, but the NER model, named entity recognition model, is actually fine-tuned Roberta. It's not an LLM. And we specifically use a smaller model for the sake of performance. So.
Okay, thank you. Would you say LLMs are like a magic sword, in that they can be used for good, but no one knows how it works? I'm hoping not, because we should know how they work. But what's your view?
Like many times we have code, like ordinary code, and we don't know why it works, right? And okay, so no joking. we at least know somehow how they work. Okay, of course, like we can consider them as black boxes, but we are trying to understand what's going inside these black boxes. So I wouldn't say that we have no idea what's going there. It's not like that, and like we can answer this question like from two perspectives, like technological one. So if it does work and if it can help, like okay. Like technically it's working, so we can use it. And from like more philosophical perspective or ethical, that okay, we are not exactly sure how it's going on. So there can be some hidden biases, for example, or like this hallucination can go on. And if we will not tackle with this one, like there are some challenges or there are some drawbacks that like can be present. But since we are aware of them, and we will not like blindly use everything for like LLM for everything, I suppose that it's okay to use it, just to be aware that like, where are borders and that don't trust like blindly what LLMs generate.
Okay, thank you, Michal. You mentioned explainability and this way of getting back to sources several times as well.
Yes, I think it is, well, in our field, it is crucial that the analyst can actually verify where the information came from. So I think it's a good practice to clearly mark any information that has been generated by an AI model. So we do that in our products. So the analyst knows that, okay, so this is not an observed thing, but this is some kind of induction. Yes, and I think that's it. Yeah, I mean, so for the users, I think it is not completely feasible to understand how the model works on the inside, and I don't think that we can expect this from the users. So it's up to us to choose the models that have reasonable level of performance and reliability.
Okay, thank you. How does your AI approach, I assume this is a question for Michal, differ when analyzing static versus dynamic content such as live streams or real-time news feeds?
Most of our work is on real-time feeds or near real-time. So that would be like 99% of what we do. In some cases, we do some offline analysis, but that's more an exception. We basically use the same tools. The good thing about working with something that's static is that you have time, so you can afford to use a bigger model or use a different technique, but it really depends on the particular case.
Thank you. Could you compare human-made and AI-made disinformation? For example, the believability, quality. I think this is more for Ivan.
Yeah, that's a very good question. Like we didn't do some kind of systematic analysis of this, and probably it's not only like it's highly multilingual, like a combination of technological and social sciences. Like so it's very difficult to find a like appropriate answer on this. But like what we like saw at what ChatGPT can actually like generate, it is highly believable. So if you will see it at the internet, and also if you will not generate only in English but also in our smaller languages, it's very probable that somebody can actually believe it, and it would be very difficult to distinguish it from human-made. And this is also because large language models are extremely skillful in providing good argumentation. So, and hallucination, what we usually consider as a drawback of large language models, is like a vital function here, because they can hallucinate any kind of evidence, events, studies, whatever you need, like persons, experts, like whatever you need. So many times, like creativity of these large language models can be like even worse as what a human can do. Not speaking about how cheap it is, how fast it is, and how you can even like personalize that content for like some particular audiences and platforms even.
Yeah, I believe many of you have already experienced it firsthand, when you try to get ChatGPT to generate something that doesn't simply exist, and it can be very, very persuasive. So yeah, have some fun after Better AI Meetup and try it. Have you tried advanced RAG techniques like RAG, CRAG? That's probably for you, Ivan, as well?
Yeah. So as I presented, so far we work only with small language models just for embeddings and doing a simple similarity match. And we are just starting to work with these RAGs, so we don't have any kind of findings or results that I can say at this moment. Definitely either active or corrective RAGs can be helpful because we are working with a quite huge possible databases or knowledge bases. Only that database of fact checks that I mentioned is containing more than 400,000 fact checks in many languages. So it would be quite difficult to select the most relevant content. But yeah, this is something what can be useful. But sorry, we don't have findings at this moment. And there is also RAG 2.0 introduced just a short time ago, so there are many of these techniques, yeah.
Okay, thank you. What kind of partnership models, and this is probably for Michal, do you envision between AI developers and media organizations to combat disinformation? I think this is actually a question that occurred to me, maybe as a first of one, because I used to be a journalist. So how do you actually see, let's say, how can AI help journalists to combat misinformation, perhaps spot fake info and so on?
I think that one obvious thing would be to have a system like Ivan presented, so basically something that can identify the existing fact checked. So that might be, and it's actually already deployed, of course, with many fact-checking organizations. So that is again about increasing the productivity of the journalists, so they don't have to manually look up the fact checks and they get all the information very easily. So I think that's a productive type of relationship. Sharing data, of course, is always a good idea. Media organizations typically have large databases of text, typically with some human annotations. So these are useful for researchers. So this kind of things I think would be most productive right now.
Yes, and another question that's probably also for you. How can AI be utilized to predict and preemptively address emerging threats in cybersecurity before they even manifest in the real world? And maybe even, can it be used for it?
So I'm not sure if you're talking about cybersecurity or information space. So in Gerulata, we don't do cybersecurity much. That was what I was doing in my previous work. So I'll talk about what we do in Gerulata, and this is a very typical use case. So our clients need to identify a threat as it emerges, not like a month after or a week after or even a day after. Is maybe sometimes too late, because once the public has been exposed to some kind of a narrative, then it's very difficult to kind of change their opinion. So it's better to react fast. And yes, so AI can help in many ways. So it's different kind of classifications that again increase the productivity of the strategic communication personnel. So they can actually see what kind of narratives are growing fast in the information space. For this, on the technical side, we can use different techniques. We can use embedding, clustering, basically semantic clustering, where we, if a narrative is spreading, it's usually spreading in various in different variations or through different channels. So we can use AI to embed this, and then use a vector database to to query it for clusters. And once we do this, we can say that what is trending, what kind of content is trending, what kind of narratives are trending right now. So this is an approach that seems quite productive to us.
It sounds like fighting a virus or something like that.
Predicting is difficult, of course. The network, the knowledge graph data can help with that a lot. So once you capture narrative and you have a location in the knowledge graph, then you can predict that if it will be viral or not, because you have additional information about the structure of the information space. Yeah.
Mm-hmm. Thank you. I like this one. It's like from some sort of productivity guru. Let's say you have a personal knowledge base, a few thousand nodes. How do you extract most value from them? How to create a knowledge graph from them? I think we already have programs for that, actually.
I think so. But if it's just a few thousand of nodes, you can just use a model that has large enough context window and put everything there. I think that's the easiest. You don't even have to have any system. I have maybe that's on the side note, but it's related to this question. There was a project on the internet that I liked very much. There was a guy who basically had a audio recorder with him all the time. He was recording all his dialogues during the day, and then in the evening he came to home and dumped the audio file, processed it through Whisper into text, and loaded it into an RG system. So basically, he had a log of everything that was happening in his life. He could look up every conversation, anything, and then he was building some additional functionality on top of that. But that was kind of cool.
Yeah. Sounds fascinating and scary at the same time. Yeah. How can the general public use AI to identify disinformation? Yep. Do you have any tips?
I wouldn't recommend general public using AI to identify this information.
Yeah, that's very difficult. Like in our projects, we primarily aim at media professionals, and that's one reason for that is that we can train them to use AI for this. And we see that even with media professionals that are with a very high media literacy, very skillful in many topics, and they are trained, for example, to fact check this information, it's very difficult for them to use AI. For example, when you have detectors of generated images. So it's so difficult to interpret the outcomes of existing detectors, because you can show them various heat maps and this kind of information. And also researchers and AI developers are not able to interpret this in a clear way, and how to communicate it to not even general public, really, media professionals, and to also communicate the accuracy and the probability that the results are correct. So it's very, very, very difficult.
Yeah, I have to say we see this similarly in biometrics as well. It's like when you show that two faces are probably identical for 0.73, probability, is it a lot? Is it, is it okay? Is it just enough? Yeah, it's very difficult, I see. Is the nature of disinformation changing in any way? From simpler text, we are going to very elaborate articles that can sound reasonable even for a smart person. I think, Ivan, you had the example of actually producing a whole scientific articles by AI.
Yeah, that's what's happening here is that the format of what is general, or not the general, but disinformation in general, is not changing to more complex ones, because typically you want to flood social networks with this information, and that content doesn't necessarily need to be very smart, right? So you just need any kind of content that can heavily support and promote your narrative. And when we take a look at what can LLMs generate, it is too good for social networks. So you usually need to introduce some kind of grammatical incorrectness, etc. So it looks more plausible that this was actually written by a real person. But it's like that. So I wouldn't say that the actual disinformation content is evolving into more smarter ways. But like what can happen here is that with LLMs, it will be much easier to generate in a huge quantity. So not a quality, but a quantity may be an issue. So like, yeah.
Okay. Which GPT model did you use when comparing the paraphrasing with the human? I think this is for you as well.
It was ChatGPT.
Okay.
But if I have one more sentence, I can just say that I suppose that the very similar results can be achieved also with other models, because it was very simple, simple task. So you can use any kind of large language models that is fine-tuned to follow instructions and can do paraphrasing. So like basically you can use anything.
Okay. Have you compared the accuracy or suitability of Roberta embeddings with current OpenAI ones? I think this is for Michal.
No, we haven't actually. We never used these OpenAI embeddings. I believe these are the other embeddings. Haven't compared it. I think there must be some benchmark. Also, it depends on which Roberta, because there are different implementations of this model. So sorry, no.
Okay. And I like this question that ends up this meeting. Does the AI ever get tired of reading the same old fake news, like a human binge watching a bad TV series? I just like the image of of AI saying just, oh no, not this again.
I suppose that AI doesn't have any kind of feelings, so it cannot get tired. I don't know. What do you think?
It's a difficult question. We don't know if it has feelings.
Maybe it's just happy to add, just another same old fake news into the node in your web graph, and it's just, yeah, we have one more, so the tie is stronger or something like that. Okay, thank you for your questions. We are very happy to have you here with us on behalf of Kinit and Innovatrix and Spot. Thanks Michal Trnka from Gerulata Technologies and Ivan Srba from Kinit for their inputs. And I'm hoping to see you in June with us. And before that, please don't forget about the AI Awards, which are given out on 30th of May at Forbes Business Fest. I will be very happy to see you there. So thank you and goodbye.